we finished the almost all the part of the electrophilic addition of alkenes. So we talked about dihalogen addition, hydration, and the reaction with alcohol, so which is a variation of the hydration. All right. So particularly the halohydrin formation, that is, so you use dihalogen as reagent, but you run the reaction in water. So the reaction is intercepted by water. So you have a CO bond and a carbon halogen bond formation. So we also talked about oxymercuration, demercuration, a two-step procedure that can be viewed as a Markov-Nikov hydration reaction. Okay, and at the end of last lecture, we talked about hydroboration, oxidation reaction. So I'm going to go over again to talk in more detail to help you understand. All right. So things to keep in mind: the problem set number 3 is open. So it is open from September 25th to November the 13th. Okay, so a quite long time. And I have to mention that some of the problems in that problem set hasn't been covered yet. Okay, so the problem set deal with some questions or some problems in following chapters, like the delocalization or aromaticity, something like that. So it is not a hurry for you to finish the problem set 3. But if you go to problem set 3 and see some problems that you can solve, you are recommended to do so. All right. And when you submit your problem set 3 assignment on Moodle, remember to put your name and your UID on the document you submitted. And it is required that you submit your assignment, the finished problem set, as a PDF file on Moodle. All right. So the midterm is October 9th. So I have started to work on the problems you are going to solve in the midterm, and it's 2 weeks apart, exactly 2 weeks apart, I think. Yes, yes. So so you guys need to hurry up, okay? So don't wait until the last 2 days to start to review the whole all the lectures we have talked about and all the knowledge we have talked about. All right. So at the end of the last semester, so we started the hydroboration, oxidation. So let me review it in detail. So the step 1 is the hydroboration using borane and react with alkene. You can see the B and the H. This bond is broken to add on the same side of the alkene to form here. And you can see after one BH bond is broken, there are still 2 BH bonds left, right? So it can happen 2 more times. So 1 more time to here, okay? CB bond, CH bond. And the 3rd time here, CB bond, CH bond. All right. And the addition is syn addition, which is a concerted mechanism. So these 2 arrows happen together to form this one. All right. And because it's a syn mechanism, so it's a syn addition to the same side of the alkene. And it's an anti-Markov-Nikov addition because the H will add to the carbon with fewer H. So in this case, you can see the H goes to the one with the methyl, the one with only 1 H, right? And the B goes to the carbon with 2 H's. So so this results from the crowdedness of 2 intermediates, the comparison between them. So in one side, you can see the Markov-Nikov addition was resulting in the BH2 motif quite close to the methyl one. All right. But the other one is not crowded at all. So this one is much favored, which leads to the anti-Markov-Nikov addition product. All right. So this is particularly important when you are dealing with some starting material that's unsymmetric, right? Like this one, like this methyl cyclopentene. So the B adds to the less steric hindered one. And it is also because it's syn addition. So the B is anti to the methyl here because the B is syn to the H here, all right? The B and the H are on the same side. And like before, if it happens 3 times, what you get is this one. And we also talk about that the third one is the most regioselective because the boron of the third reaction is the most bulky. And you can imagine if this boron is very bulky, this is very unfavored. So that's why we can use 9-ppn, the boron with a very bulky substituents. In this case, the boron will have a huge clash with the methyl here, which would eventually lead to the anti-Markov-Nikov addition. Okay, the oxidation, we slided through it quite briefly, so I'm going to talk about it in detail. So the boron at the beginning is the neutral boron, which has an unfilled octet, and this will react with a nucleophile, which in this case is the peroxide anion. And once it attacked, it will form an anion, all right? And the second step is what we call a 1,2 alkyl migration. All right, and the alkyl migration is very important in stereochemistry because what we observe is the retention of carbon stereochemistry. So if this CB bond is pointing back to the paper, this CO bond, the resulting, will also be pointing back. All right, so the stereochemistry of the previous hydroboration step is totally reserved in this oxidation step. So the whole process of hydroboration oxidation, the stereochemistry is decided by the hydroboration step, okay, which is the syn addition, as we mentioned. And then you can imagine this process will happen 3 times because we have the 3 CB bonds, okay? The second time, the third time. Now you get the borate ester, all right? Then the borate ester will eventually become the alcohol to release this alcohol, all right? So the mechanism is that the hydroxide, which we use a sodium hydroxide here, the anion will attack the B again because it's a neutral. And once we form this negative boron, then this will leave. The alcohol will leave and to become this alkoxide. And under the condition of water, it will be protonated and eventually get this. Okay, so imagine. So this oxygen position is used to be boron's position. Okay, here it used to be B. Okay, in the previous one, B. So if B is pointing back, the O is pointing back. So if B is syn relationship with this H, this OH is now syn with this H. Okay, so just keep in mind these mechanisms and really understand why this is a anti-Markov-Nikov addition selectivity and why it's a syn addition. So all these results of stereochemistry has a mechanistic support or mechanistic reasons behind it. And if you understand the mechanistic reasons, you understand the stereochemistry. Okay, so as I mentioned here, syn addition is because this is a concerted mechanism for membrane, right? And the Markov-Nikov is because the anti-Markov-Nikov selectivity is because the boron has to stay away from the methyl, the substituents here. Okay, and this step determines it's a syn addition and the anti-Markov-Nikov. And the next step doesn't change anything of the stereochemistry. So the stereochemistry as the same as the first hydroboration. So the overall syn stereochemistry and anti-Markov-Nikov regioselectivity. So if we go back and compare these two type of two-step procedure for the hydration reactions, so they are quite different. So both of them are very useful because it doesn't go through a carbocation intermediate, which would rearrange. So in these two reactions, it doesn't rearrange. So in that case, what we get is what we want. Okay, there is no accident, and everything is what we expected. Okay, so for the oxymercuration and the demercuration, it is syn. All right, and it can also be anti. All right, because because this mechanism, if you go back, if you still remember. So because the step 1 plus step 2 is a anti-addition of the mercury and the the water. But the third step messed that up. Still remember that, right? Because the third step is kind of like a radical mechanism. Although you establish a quite good stereochemistry, the anti-addition here, the carbon mercury bond will be, the stereochemistry here will be destroyed. So it will be messed it up. So for the mercury reactions, it can be syn and the anti-addition. It's a mixture. But for the hydroboration oxidation, it is syn. Okay, because the oxidation step doesn't destroy the stereochemistry of the hydroboration step. All right, so these are both syn. Okay. All right, so after the electrophilic addition and all these two-step procedure to equivalent to the hydrogen reactions, so we are going to move into other part of this alkene reactivity, which deals with oxidation reactions and the reduction reactions. So as we talked at the very beginning, we said there are 4 types of reactions, but how about oxidation and reduction? So what I want to state here is that more than one of these classifications can be applied to a reaction. So there can be a reaction that are, let's say, addition reactions. Okay, 2 molecules combine, but it can also be an oxidation reaction. So it is both an oxidation reaction and an addition reaction. That is quite possible. Okay, and there are also possibilities that the reaction is addition, but no reduction or oxidation happened, right? It's just a purely an addition reaction. So that's quite possible. So you can't say, oh, this is addition, this can be oxidation, can't be oxidation. So that's just wrong, okay? So in inorganic chemistry, as some of you have learned, that we say the oxidation occurs when a metal loses electrons, okay? So if you react magnesium 0, and you get it to magnesium 2, like magnesium chloride, then you say it's oxidized because the metal, the magnesium, loses electrons. It becomes a +2, 2+, okay? And we say reduction on the reverse way, right? So this is manganese and manganese 7, right? +7. And then this is manganese +4. Okay, so the manganese oxidation state decrease and it gains electrons. So we say it's a reduction. Okay, but in organic chemistry, so we usually do not express the oxidation state of carbon numerically. What does that mean? So we don't say, oh, this carbon is +4, this carbon is like 0. So we don't say that a lot because it is usually quite hard to differentiate. So between the oxidation states of carbon, because carbon is usually connected to other atoms, you know, through a covalent bond, and it doesn't really exist as metal ions do. All right, so there is no carbon 2+ like cation. Okay, there is also we barely say, oh, this carbon is -2. All right, but how we differentiate between whether a carbon's oxidation status is that they're what we call the oxidation levels. Okay, so functional groups are usually associated with specific oxidation levels. So although we don't have a numeric number for those oxidation levels, but we, as organic chemists, we are very clear about which is higher in oxidation level. Okay, let's say. So this is the carbon dioxide is probably the highest. The molecule, the carbon molecule is the highest oxidation state because it's linked to 4 CO bond. Okay, a CO double bond and a CO double bond, and it's clearly higher in oxidation level than a carbon linked to a carbon with 3H. All right. And you can see all those molecules between these 2 extremes, okay? So you can see some of them are linked to oxygen, some of them linked to chloride. You can clearly see if it's linked to more oxygen and more chloride, the oxidation level is higher. So, so if we keep these molecules' oxidation level in mind, then we can kind of define what is the oxidation or reduction reactions of the organic molecule. Okay, So what we say in organic chemistry that is different from inorganic chemistry is that we define oxidation and define it occurs when there is a loss of electron density at the carbon. So usually this means that when carbon becomes bonded to more electronegative atoms, so it's an oxidation. So let's say if you start from CH bond, okay? For example, like the ethane has a lot of CH bond, right? And then if during the reaction, the carbon is now linked to more electronegative atoms, like if a CO bond is formed, or CN bond is formed, or carbon-hydrogen bond is formed, then I look at the oxidation level, and you can see, oh, now the C is bonded to chloride, okay? So when it is bonded to more electronegative atoms, the electron density, because of the electronegativity of the atom it is bound to, becomes less. Okay, so there is a loss of electron density on carbon. So in this process, we can call it an oxidation. Okay, and reversely, the reduction occurs when there is a gain of electron density. So if the starting material has the carbon bonded to a very electronegative atoms like nitrogen, oxygen, or hydrogen, all right, then if at the end it becomes a CH bond or CC bond, then we say there is a gain of electron density, and because it is bonded to less electronegative atoms. So what does that mean? It means if this carbon bonded to a lot of oxygen or chloride become back into the ethane, okay, or it becomes bonded to smaller number of electronegative atoms, we say it's a reduction. Okay, so to show you an example, for example, if we have methane, okay, react with chlorine, it is a substitution reaction, right? So if we say substitution reaction, we can say, okay, parts from two molecules exchange. So this H gives to chloride becomes HCl. This chloride gives to the carbon, now become here. Okay, it's a substitution reaction, but also because the carbon originally bonded to H, now bonded to chloride, it's now bonded to more electronegative atoms. So this is also considered an oxidation. So this reaction is both an oxidation and a substitution reaction. And another example, so we have also a way to reduce or what we say transform this carbon chloride bond back into the CH bond. And the H is the less electronegative atoms. So this is a reduction reaction, right? So in this case, we use magnesium, which you will learn in the next half of this semester, which goes through a Grignard reagent, and the Cl bond becomes CCH, become a CH bond. Okay, it's reduction reactions. Okay, let's start from a more complex situation. If we have an ethylene and we have addition reactions, okay? So let's say ethylene react with the H2. Now 2 CH bond is formed from CC bond, okay? And we need to consider the overall electron density change of both alkene and both alkene carbon atoms. Okay, so we consider this a reduction reactions because 2 new bonds formed between carbon and a less electronegative element, which is hydrogen. So it's considered a reduction. How about reaction with bromine? All right, so this 2 carbon originally is forming a pi bond between each other, so CC bond, right? And then at the end, we have 2 C-bromide bond formed. Okay, and bromide is, as you know, very electronegative. So this is considered an oxidation. So 2 new bonds formed between carbon and a more electronegative atom. So how about those reactions we just learned in the earlier part of this chapter? So addition reactions, either with water, hydration, or with the HX. So in this case, 2 CC bond, these 2 CC bond become a 1 CH bond and 1 CBr bond. Okay, Br is more negative, but H is less electronegative. So in this case, It's neither oxidation or reduction. Okay, so you have to see the overall, and you shouldn't just focus on one of the carbon. You should focus on two of the carbons. So in this case, it's one UCH bond and one UCBr bond. So overall, it's not redox. So and it's reasonable, right? So I told you a joke, right? Like the hydration is just like the alkene drinking water. So hard to imagine there is any oxidation or reduction happening. Okay, so for the detailed types of reaction we're going to learn, we're going to start with the hydrogenation. Okay, so overall, as we talked about, it's a reduction. So, but the reaction is thermodynamically unfavored. So, and the reason is that two new sigma bonds here, the CH bond, is energetically favored than one pi bond. Okay, so it's thermodynamically favored. All right, so so energy-wise, so this is much lower energy than these combined. Okay, but there is no spontaneous reaction. So as we say, when we consider a reaction, we not only need to consider the thermodynamics of the reaction, we need to consider the kinetics of the reaction. Okay, so thermodynamic consideration is based on eventually, if give it enough time, give it enough energy, so what's the terminal product is going to be. So in this case, it's going to be the reduction product. Okay, but kinetically, there is no spontaneous, meaning although the reaction is thermodynamically favored, energetically wise, its activation energy is quite high. So that means that it might take like thousands of millions of years to finish this reaction. It's not fast enough. Okay, so in this case, if we just combine ethylene and hydrogen gas together, nothing will happen. Okay, even if the energy-wise the product is more stable. Okay, so so again, so if it naturally won't happen, there is a possibility that we can add a catalyst to lower the activation energy. So you can see the starting material is higher in energy than the product, right? So it's thermodynamically favored because the Gibbs free energy change is negative. Also, the heat is negative, so 120 kilojoule per mole. All right, but it won't happen because the activation energy is too high. Okay, so although this is lower, but it had to climb a huge hill. Okay, to overcome the barrier and run down. All right, so the catalyst the industry has found about to make this very slow reaction faster is, for example, the platinum or palladium on carbon. So if I write this like PD/carbon, means it's a catalyst and it's a palladium on carbon catalyst. Basically, so what people find out if they put like a palladium atom like on a carbon, like the graphene or something like that, like the carbon powder, just put it on a heterogeneous way. Okay, so they found it is a very, very active catalyst. But you just need to remember that the palladium/carbon is a very good catalyst for the hydrogenation, right? And the way it operates is that it decreases the activation energy of the hydrogenation. So now it's not only it's thermodynamically favored, the kinetic barrier, the activation energy is much lower. All right. So what's the mechanism? So because as I said, it's a heterogeneous catalyst. So basically, it's a surface of carbon that is all carbon or palladium. All right. So this is so the hydrogen, if it approaches the catalytic surface, it will become more reactive as each atom absorbed on the metal surface. Okay, this bond you can see it's broken. Now it's a very active hydrogen atom, and then the olefin or the alkenes can also approach the catalyst surface. In this case, I will be very close. It will also be activated. Then the first reaction happens when one of the hydrogen atom will be transferred to this carbon. Okay, and then this side is open now. Okay, and this carbon is still connected to the catalyst surface. All right, and the next reaction will transfer another hydrogen atom into this carbon. All right. So just remember, because this reaction happened on catalyst surface in a stepwise, and once the first is connected, first hydrogen is connected, the second one will be on the same side. Okay. So it's overall a syn addition. So although this mechanism is just for your interest and do not require you to understand the detail of it, but you need to remember that you need to memorize that the hydrogenation is a syn addition. So you can see if the hydrogen under the platinum catalyst and it is added into the 1,2-dimethyl cyclohexane, all right, and the two hydrogens here will be on the same side. Okay, it's not anti, it's a syn addition, and the product is cis 1,2-dimethyl cyclohexane. All right, and selectivity wise, so there is something we call the chemoselectivity here. So as this double bond is we consider unsaturated bond, right? So this H2 can add into this double bond to here. But later you will also learn that the CO double bond or this ester is also unsaturated molecule, okay, unsaturated motif. But under the palladium carbon or platinum catalyst, the hydrogenation only happened at the carbon-carbon double bond. Okay, this chemoselectivity is quite important because when you try to devise some synthetic route to a molecule, so you need to understand, okay, the hydrogenation won't happen on the CO double bond, CN double bond, or ester or ketone, and it only affects the carbon-carbon double bond. Okay, so this is the chemoselectivity of the catalytic hydrogenation. And as we said, it's a syn addition, and then if different stereoisomers, like in this case, it's a cis and it's trans alkenes, it will give different stereoisomers. So this is we call the stereospecific reaction. Okay, and the two stereoisomers gives two different stereoisomers as product. Okay, so in the cis, if it reacts at the top phase, it will become here. All right, the H is here. If it reacts at the bottom phase, so the H becomes here, and these two are enantiomers. Okay, and if it's a trans alkene, so if it reacts here, so now the 2D atom will be on the one is pointing back, one is pointing up in the front, so instead of here. Okay, so this and the product from the bottom phase attack of the hydrogen is enantiomers. Okay, and if I ask you see what's the relationship between this one and this one, can you figure it out? Yeah, it's a diastereomer, right? Okay, so if you still remember, there is also like the so there are examples of alkenes react with electrophiles, and also is a stereospecific that we talked about, if you still remember, and you need to keep in mind the concept of stereospecificity, and just remember the hydrogen here, and due to the mechanism it has, it's stereospecific reactions. Okay, and how about oxidation? So after we talk about the reduction, oxidation is another category of very important reactions in the reaction of alkenes. Actually, in the introductory organic chemistry, like this course, it is not well focused on the oxidation and the reduction. But in more difficult courses like integrated organic synthesis or organometallics and more frontier of chemistry, oxidation and the reduction of the alkene are really important reactions in building some complicated molecules, not like simple molecules we are focused on in this course. Okay, so we have several types of oxidation. So this course is going to cover the dihydroxylation, epoxidation, and the other the CC bond breaking oxidation, which is ozonlysis. We'll talk about it. So so if we catalog if we classify these oxidation reactions from the as it's different from the reduction because two new bonds formed between the CO bond, which is the oxygen is more electronegative. Negative, okay, so the carbon becomes bonded to a more electronegative atom. So this can be this is oxidation, okay. So for the epoxidation, it's also two new bonds formed between carbon and oxygen. But what we get is this string membrane instead of this open chain product. So the string membrane has the two CO bond, all right? And because the carbon is now bonded to a more electronegative atom, so it is also considered an oxidation, okay? And again, hydration, drinking water doesn't oxidize or reduce you, right? So although we form the CO bond here, we also form the CH bond. So overall, if you consider both of the carbon atoms, it's neither oxidation nor reduction reactions. All right. So let's go to the dihydroxylation first. Okay. So what you need to remember, so the net process is the syn addition. So like the hydrogenation, two hydrogen adding to the same side. Okay. And the dihydroxylation is also syn addition. So the two CO bond is formed on the same side of the alkene. All right. And the mechanism. So why is it a syn addition? So the reagent we usually use for the dihydroxylation is called osmium tetraoxide. So OSO4. Okay. This molecule looks like here. So osmium is attached to four oxygens, and each of them form a double bond with the osmium. So to remind you that you may learn some octet rule, right? Because osmium is kind of like it is the transition metal, so it can form more bonds, and it can have more than 8 electrons on its shell. All right, so it has d electrons. All right, so it can form a lot of bonds. So don't be surprised. Okay, if it's a transition metal, it can form like all these bonds. Okay, so the way it forms a CO bond with the olefin is through a concerted, and syn addition. Okay, and you can see all these three bonds is forming together, concerted. So you can see this double bond, which has electrons, will attack this oxygen. And this osmium oxygen double bond is broken, give back the electrons to the osmium. And the osmium now have more electrons than it needed. So this osmium oxygen double bond is also broken to attack this carbon. So then the process is that a form of fine membrane, what we call osmate ester, okay, through this concerted one-step mechanism. Now you can see through a one-step mechanism, both CO bond is formed, right? Magic-like. Okay, and then to get our product, the osmium ester must to be broken down. Okay, how it is broken down is through the water. Okay, the water is nucleophile, now attack the osmium, replace one of the osmium oxygen bond. Okay, now one bond broken. Okay, one osmium oxygen bond is broken. And then the next mechanism is that another osmium oxygen bond will broken by exchange of these bonds. Okay, this becomes double bond, this bond broken. Okay, so the overall process is that the olefin is dihydroxylated in a syn addition because this is concerted and it can only happen together on one side of the olefin. It's a one step, two bond formed syn. Okay, understandable, right? Okay, so and the net result is also that the osmium originally bonded to 4 oxygens in double bond pattern. Now the osmium is bonded only to 3 oxygen atoms, and each of them is still a double bond. Okay, so if you count the oxidation state of the osmium at the beginning, it is osmium what? So each oxygen is -2, right? So the osmium at the beginning is 8+. Okay, and the osmium at the end is osmium 6+. Okay, so for the osmium, it's reduced right? It turns from osmium 8 to osmium 6. Okay, it's accepting electrons. And for the olefin, it's oxidized because the carbon is bonded to more electronegative atom. Okay, and based on the mechanism, because only osmium tetraoxide can catalyze the reaction. So at the end of the reaction, this osmium is not reactive at all, right? It needs to have 4 oxygen to do the reaction. Okay, so stoichiometric amount osmium tetraoxide, meaning if you have 1 equivalent of the olefin, you need 1 equivalent of the osmium tetraoxide to do the dihydroxylation. And the osmium trioxide is the terminal form, right? But the bad thing, really bad thing about osmium tetraoxide is highly toxic and expensive, very, very expensive actually, and very toxic. Okay, so what people figure out is that okay, the dihydroxylation reaction seems very useful, highly applicable. Okay, but the thing is that we cannot afford to use so much amount of osmium tetraoxide, and people die if they mishandle the osmium tetraoxide. So we want to make it a catalytic amount. So if we use 1 equivalent of olefins or alkenes, we only want to use like 5%, okay, of osmium tetraoxide. That's it, okay? That's cheap, okay? 5% is cheap, but 1 equivalent of osmium tetraoxide is unaffordable. So people are genius. So what they figure out is that, okay, so after 1 catalytic cycle, the osmium 8 is reduced to osmium 6. Okay, instead of adding more osmium 8, can we use some oxidant, like external oxidant, to reduce the terminal osmium 6 back into the active osmium 8? So you see the trick here. So instead of adding 1 equivalent, we just need to recover this part, right? So during the reaction, if we add an oxidant, then in situ, oxidize the osmium 6 back to osmium 8. Okay, so if the oxidant itself is quite cheap, right? We just need to use catalytic amount. It will just turn around. So 1 osmium can eventually catalyze the reaction of like 20, 100 of the dihydrogenation of olefin, right? So what people found out is that this what we call N-methylmorpholine N oxide is a very good oxidant to recover the osmium 6, oxidize it back into the active osmium 8 that can do the dihydroxylation. Okay, so the and it will be reduced back to the N-methylmorpholine. Okay, so how does that work? Okay, so you can see we have catalytic amount of osmium tetraoxide from the osmic ester, and then from the dihydroxylated product to osmium 6. Okay, the thing is that the NMO, this thing, can transfer 1 of the oxygen to osmium. Okay, it only has 3 now, but once it reacts with NMO, it gets 4. Now, if it gets 4, it can redo it, right? It can redo the dihydroxylation, and this one loses an oxygen and becomes this one. Okay, so that means the stoichiometric amount of oxidant in this dihydroxylation, this catalytic osmium dihydroxylation, is actually NMO. And the osmium can be turned around between 6, 8, 6, 8, like many times, and facilitated by this stoichiometric amount of oxidant. Okay, and so if you see the net process, it's you can only use only 1% of this osmium compared to here. You just need to use the 1 equivalent of the NMO, all right? And NMO is not as toxic as osmium tetraoxide, and NMO is very, very cheap. Okay, so this is how we achieve applicable and useful and cheap oxidation by turning the osmium from the stoichiometric amount to the catalytic amount, which is really genius, and which can be seen in a lot of reactions in organic chemistry. But in this course, we only cover this part. But eventually, if you see, okay, one reaction with catalytic amount and it involves the redox reaction, and you can try to see, oh, okay, then what's the stoichiometric amount of oxidant or reductant here? Let's find it out. Okay. All right, then we will talk about epoxidation reactions. So as I talked that the epoxidation, instead of forming a open chain 2CO bond pointing out, it will form a quite strained string membrane. And if I ask you what type of string it does have here, can you name the string name? Like, why is this a string molecule? Angle string, right? Okay, because it's a string membrane. Because this OCC bond, this sp3 carbon, the bond angle is like 60 degrees, but its optimal bond angle should be 109.5 degrees, right? And the angle deviated from the optimal angle, so it has definitely the angle string. All right, keep that in mind. All right, and that's from chapter 1 to 3, and it's a good time for you to start reviewing that. Okay. So the next process is what for here epoxidation. What we use is called peroxy acid, or abbreviated per acid. Okay, you probably know carboxylic acid, right? Which is RCOOH, right? But now we have two O here. Okay, we have an OO bond, oxygen bond, and this is highly oxidizing. Okay, so one very prominent example of this type of a per acid, and in lab uses, we use this a lot, is called the metachloroperoxybenzoic acid, abbreviated as MCPBA. Okay, it has 3 position chloride substituents on the benzene ring, and this can epoxidize olefins to give this epoxide. All right, and once the oxygen is transferred into the olefin, okay, so this per acid lost an oxygen, right? It becomes acid. So this MCPBA is the stoichiometric amount of the oxidant, and its terminal form, a reduced form, is this metachlorobenzoic acid, which is MCBA. So this is acid. So the per acid becomes acid, olefin becomes epoxide. Okay, so another thing about selectivity, we say that dihydroxylation is syn because it's concerted. The 2O or 3CO bond form at the same side at the same time, right? And the epoxidation is also syn addition because the mechanism requires so. And it's also because a trans epoxide doesn't exist. Okay, so imagine if you have a CO bond pointing to you, but another CO bond is pointing back. It can't, right? Because string membrane has to be a plane. Okay, you can't have a 3D structure of a string membrane. And the mechanism. So like the dihydroxylation, the mechanism is also concerted, meaning 2 CO bond is formed at the same time. Okay, so what does it do? So this oxygen is quite electrophilic, and the olefin has electrons to share. Okay, the electrons will boom attack this oxygen, and the oxygen, to keep the valency, will broke this weak oxygen bond to here, and to keep the valency, the CO double bond broke to grab the hydrogen, and the hydrogen, to keep its valency, the HO bond is broken to attack this carbon. All right, quite fancy concerted mechanism with the 4 arrows together. So the net result is that we transform the yellow oxygen to the olefin, and it's a syn addition. Yeah, only the syn addition is possible, okay, because it's concerted and through membrane planar structure. And through this process, the per acid loses an oxygen, but keeps all the other atoms with it. So it becomes a carboxylic acid. Easy, huh? So the final oxidation reaction I'm going to talk with you is called the ozonolysis. So ozonolysis is a little more complicated than the dihydroxylation and the epoxidation, because not only the oxygen is transformed, the CC double bond of the alkenes, it is broken. All right, so let's just look at some reactions and see what's the rules or what's the principle here. Okay, so let's just ignore the conditions first. Okay, 6 membrane olefin cyclohexane, okay, become this open chain with 2 aldehyde. So what changed? So I draw it to just let you see the change. Okay, we have 1, 2, 3, 4, 5, 6. Oh, carbon number doesn't decrease. Okay, and we have 2 more hydrogens, and this carbon-carbon double bond apparently broke, right? Okay, these are not connected. So we have 2 more oxygen, and carbon-carbon bond is broken. How about this one? So we have a double bond here. Okay, so this CC bond also broke. The CC bond broke to form a 2 molecule, 2 ketones. Okay, the carbon is now connected to an oxygen double bond. This carbon is also connected to a CO double bond. All right, let's see the third one. So this 1,1 disubstituted olefin, the net result, okay, it broke. The CC double bond broke. All right, 2 molecules now. Okay, this carbon, look at here, it forms a CO double bond, and this carbon also forms a CO double bond. All right, and this molecule doesn't break into 2 molecules because it is inherently linked. All right, so the net result of the ozonalysis is that CC double bond broken, and the carbon used to form the CC double bond is now linked to the CO double bond. All right, then we'll look at the mechanism of it. So how do we generate ozone? So some of you may know those like 20 years or maybe 10 years ago, 20 years ago, we have those kind of a popular concept is that ozone is actually good for you or something like that. Then you have those kind of small instrument machine that they sell to your home, and you can turn it on, and then it will ionize the air and to generate the ozone, and it smells funny. Okay, and so the mechanism behind that is that the oxygen can be turned into ozone by electric discharge. All right, and the ozone is a very active species, will react with alkene to form what we call the mole ozonide. Okay, which is quite funny looking. Okay, 3 oxygen here, and it will rearrange to form ozonide, and then we have a reductive workup to get rid of the fine membrane and get 2 molecules. So the net result is that this carbon CO double bond, this carbon CO double bond. Okay, and the detail mechanism. All right, I know this is a little bit complicated for many of you, and but try to understand it. All right, so ozone, what does ozone look like? Ozone looks like this: 3 oxygen bonded together. All right, and we have oxygen-oxygen double bond and the oxygen-oxygen single bond. So that means this oxygen bearing a positive charge, and this oxygen is negative charge. All right, so because this is positive charge, the olefin will attack this oxygen, breaking this bond. Okay, and at the same time, because this becomes partially positive, the oxygen here will attack here. Okay, it's a concerted mechanism with 3 arrows together to form this mole ozonide. All right, then the second step is the CC bond breaks. Okay, so this oxygen share gives electron to here. Now this bond break. This used to be the olefin. Okay, this bond breaks to form a CO double bond and break this OO single bond. All right, to give these 2. Okay, and now the second cyclization, different from the first one, happened to generate the ozonide. Is that now we have a polarized CO double bond, which is partially positive here, and we have oxygen bearing a negative charge that will attack here, and this bond break to attack here, and this bond break to attack the oxygen. It's also a concerted 3 arrows happening together to generate this ozonide, which has the 3 oxygen rearranged at different positions. All right, and then the reductive workup. Okay, zinc will attack because it has a pair of electrons to attack this oxygen, and this OO bond breaks, and this CO bond breaks to CH2. Now because at the end we have 2 carbon bonded, each bonded to 1 oxygen double bond, and because ozone has 3 oxygens, right? What's the rest of the oxygen? It goes to the zinc. Okay, 3 oxygen of the ozone, 1 goes to this carbon, another one goes to this carbon, the third one goes to the zinc. So the overall reductive workup is that the zinc reduced this one to give the zinc oxide and the 2 carbonyl compound here. Okay, so next time I will go over the mechanism again. So if you have any questions, I will explain it again. All right, and we will also finish the chapter 5 to 6 and start chapter 7. And we also have some exercise at the end of chapter 5 to 6, and some of them are from the midterm of last year. So it's really very important for you to get familiar with all these problems from that are going to appear on midterm, right? So I think that's all for this week, and I hope you have a good week and a good weekend, and start to prepare for the midterm. All right. Okay. See you next week.